What is going on, everyone? So today's video is going to be about transistors, and the goal of this video is to get you able to know when and how to use a transistor in a circuit. So if you search on YouTube something like Transistors Explained or Transistor Tutorial, you get a lot of really good videos that go in depth and explain like what a transistor is and then like the inner workings of a transistor. But what I think there's a lack of resources on is some more like practical applications showing all the different kinds of circuits you can make with a transistor, or doing some like actual real life circuit analysis on transistors. They give you enough information and enough like working knowledge to know like when and how to use them in your own circuits. So that's going to be the goal of today's video. Hopefully I can leave you here knowing like whether you can use a transistor in a circuit that you want to build, or like how you need to go about doing that. Before we go any further though, please go ahead and drop a like on this video for me and subscribe if you'd like to stay up to date with any future videos. So with that out of the way, let's just jump right into it. So I have here a bunch of notes that we're going to go over. We're going to work some example circuits. So we'll be doing some circuit analysis techniques that we've learned in previous videos. So if you haven't watched my previous videos in this series, I would suggest going and doing that. And then we also have some circuit simulations that we are going to be going over as well. So let's just start out here with the introduction. So like many videos, I want to give a brief explanation of like what they are and kind of how they work. But this is going to be very brief and to the point. So there are two main types of transistors. You have bipolar junction transistors, or BJTs for short, and you have field effect transistors, or FETs for short. Okay. And then within the field of BJTs, there are two major types of BJTs. You have NPN and PNP transistors. So this video is only going to be focused on NPN BJTs. So we're picking one very specific type, and trust me, doing the in-depth analysis on just this one type should give you enough information to work with other ones. But if you want me to make more videos on the rest of these transistors, then drop a comment down below just saying you want me to make another one, and I'll gladly make more. So next up is the anatomy of the NPN transistor. So you have 3 pins on a transistor. You have the collector, the base, and the emitter, right? Then on the right here, we see what is a typical schematic symbol of a transistor. A dead giveaway that it is an NPN transistor is the fact that the arrow right here is pointed towards the emitter. And then here I have also labeled different currents that we'll talk about in a second. So you have IC, which is the current flowing into the collector pin, IB, the current flowing into the base pin, and then IE, current flowing out of the emitter pin. Okay, so now we're going to talk about some key operating characteristics of a transistor. This is the basis for understanding the fundamentals of how to use them in your circuit. And so they utilize things like Kirchhoff's current law and Kirchhoff's voltage law. So this is why those are extremely useful things to know. Okay, so the first key like formula or equation regarding a transistor is that the emitter current is equal to the sum of the base current plus the sum of the collector current, right? Looks exactly like Kirchhoff's current law. You have 2 currents flowing into this node, 1 flowing out of the node. So all the currents flowing into the node are equal to the sum of the currents flowing out of the node. So hopefully this makes sense. The next key equation right here is that the current flowing into the collector is equal to alpha times the current flowing out of the emitter. And then alpha is equal to roughly 0.999. So what this basically means is that you should have minimal losses between the current flowing into the collector and the current flowing out of the emitter. So this should be more or less I could call it a lossless switch. But just know the difference between your collector current and your emitter current should be minimal. So the next characteristic equation is going to be that IC is equal to beta times IB. So, and then B ranges anywhere from 50 to 1000. So I want to linger on this one for a bit because it's an important one, and hopefully it gives you like an aha moment. The collector current, so the current flowing into the collector, is directly related to the current flowing into the base pin. So let's say you had like a milliamp flowing into the base pin, then you would have like, say, like 100 milliamps. If beta was 100, you would have 100 milliamps flowing into the collector pin. right? That's exactly what that means. There's no more. That's all you need to know. And we'll see some actual applications of this in practice here, but this is like a really important one for understanding. Okay, and then this last one here is that the emitter current, the current flowing out of the emitter, is equal to 1 plus beta times IB, or the current flowing into the base. So the emitter current is also proportional to the current flowing into the base, which makes sense. And we just derived this one from previous equations. Okay. And then lastly, we have Kirchhoff's voltage law holds if you do the voltage drop from VC to VE. So if we're going from here to here, and then VE to VB. So going from here to here, and then here to here, and then VB to VC. So here to here. If you go around that loop, the voltage drop across those points is 0. And lastly, this is another really important characteristic, and this is a very typical value you see across all transistors, is that VBE is roughly 0.7 volts, right? So the voltage drop from B to E is it's a constant, and it's very often 0.7 volts, right? And we'll see that in practice more. So just know that the voltage drop from B to E is it's always a constant, and then very often it's 0.7 volts. Okay, so let's do a review of some key concepts here. So transistors are a current controlled current source. Hopefully this makes sense, because the current going into the base directly controls the current flowing into the collector and out of the emitter, which is these two equations we just mentioned. Then I have a note here: by understanding current IB, we can solve the entire circuit. So solving for the current flowing into the base pin is the key to solving every transistor related circuit. So if you can figure out IB, you can solve the rest of the circuit, no problem. Okay, so let's take a look at an example. Okay, so here you have a very typical transistor circuit where you have a voltage source going through a resistor that is hooked up to the base pin, and then you have another voltage source that is hooked up to the collector, and then that is flowing through the collector pin, into the collector pin, and then out of the emitter pin. So the way you want to break down these types of circuits is, first of all, you want to separate them into your input loop side and then what is referred to as your output loop side. So the input loop side has your like base pin, whatever input voltage or current source you're using, and then it's going to also include going from B to E, and so it's basically this loop right here, right? So it includes the voltage drop VBE, and then it includes whatever voltage or current source that you are inputting into IB. And then of course your output loop is whatever your like other voltage source is that is driving. Typically there's a load right here. In this case, there's a 100 ohm load that we're driving with this transistor. And then of course it's always a ground point at the bottom right here. Okay, so the steps of solving an equation like this are: the first one is to perform Kirchhoff's voltage law on the input loop. We want to find the base current. Okay, remember I said that the base current is the key to understanding every transistor circuit. So what Kirchhoff's voltage law on the input loop looks like is we're going clockwise. So we go minus to plus, minus 4 volts. And then this is going to be plus to minus. We have 200 kilo ohms times IB. That's what that voltage is in terms of Ohm's law. And then we have a voltage drop of 0.7 volts, which comes from VBE. So again, we're following this. We got minus to plus, plus to minus, and then we have VBE, which is plus to minus. And remember, we said earlier that VBE is, for this case, VBE, it says, is 0.7 volts. Okay, so then you have a plus 7 volt drop right here. And then you have equals to 0. So then that closes the loop right there. So then what you want to do is perform Kirchhoff's voltage law on this equation right here. You want to solve for the base current. So you get IB equals 4 minus 0.7 divided by 200 kilo ohms. And so that means we determined that IB equals 16.5 microamps. Okay, so we've now just solved for the current into the base pin. And so basically everything else should be set up for us. It should be extremely easy to solve. So then step 2 is going to be solve for the collector current. So we want to solve for the current flowing into the collector pin. So IC is going to be equal to beta IB. And we are already told at the beginning that beta is going to be equal to 50. And then we know that IC is 16.5 microamps. So then we just do the simple formula. 50 times 16.5 microamps equals 0.825 milliamps. So we know IC is 0.825 milliamps. Okay, so now we figured out IC after we calculated IB, and it's as straightforward as that every single time. Just we get IB, we automatically know IC. So then the final step is, so what we're trying to do is we're trying to solve for V out now. And so for the final step, we would then perform Kirchhoff's voltage law on the output loop, right? So we're going, again, we're assuming just clockwise by convention. So then we have a negative V out minus 100 IC plus 6, right? So that's where that came from. So negative V out minus IC plus 6 volts equal to 0. So that's Kirchhoff's voltage law on the output loop. So you just do the math on that and you figured out that V out equals 5.917 volts. Okay, and then that's all there is to it. Like I said, it's as straightforward as finding the current into the base pin, and that basically sets you up for the rest of the circuit. All right, let's take a look at another example, and this one's a little bit different. Okay, for the transistor circuit in this figure, let beta equal 100 and VBE equal 0.7 volts. Determine V out and VCE. So sorry, this is VCE right here, and then this is V out right here. So at first glance, you're probably thinking like, oh my gosh, this is totally different. What on earth do we do? And it's literally the same exact steps. Okay, step 1, perform Kirchhoff's voltage law on the input loop. We just did this. Very straightforward, right? Going around town, we get minus 5 volts plus 10 kilo ohms times the base current plus VBE, which is 0.7 volts. And then, wait for it, we get plus 200 times I emitter. Okay, so note that the current flowing through this 200 ohm resistor is not the base current. It is in fact the emitter current, right? However, if you remember earlier, we literally have an equation that relates the emitter current to the base current in terms of beta, and we were given beta, right? So again, it's extremely straightforward. So all we've done in this step is just rewritten IE as 1 plus beta, right? So now we get 2.2 e to the fourth, which is like 20,200. I think I wrote this wrong. I think it's supposed to be 2.02. So it's 20,200 times our base current plus 0.7 volts. So this is what Kirchhoff's voltage law looks like with everything in terms of the base current again. So again, we were trying to solve for our base current. So you just rearrange these, do the algebra, then you get 5 minus 0.7 divided by, this is the total resistance that we are experiencing, right? So this is just 10 kilo ohms plus 20,200 ohms. So you get 30,200 ohms. That is equal to 0.142 milliamps. That's what IB. So again, the name of the game, solve for the base current. That's what we just did right here. After that's done, everything else is a piece of cake, right? So step 2, solve for IC. We can also solve for IE now as well. We know IC is equal to beta times the base current. And in this case, it is 0.142 milliamps times 100, and that's going to be equal to 14.24 milliamps. And then we know the emitter current is equal to 1 plus beta, or 1 plus 100 times our base current, which is the same exact thing again. And so the emitter current is equal to 14.342 milliamps. So now we want to solve for the output voltage and the voltage drop VCE. So again, all we're going to do is perform Kirchhoff's voltage law on the output loop. Okay, so we have negative 12 volts plus 500 times I collector, right? So that is this right here, 500 times I collector plus VCE plus 200 times I emitter equal to 0, right? So we've just written these in terms of Ohm's law right here. And then basically what we're trying to do is VC is still an unknown at this point. Like we're not directly solving for it. We're just using Kirchhoff's voltage law to give us the missing number basically. So we have 12 volts plus 7.12 volts plus 2.868 volts. And then so you add these two up and then you're able to just subtract them from the total. And then you know that the VCE is equal to 2.01 volts and then the V out is equal to 2.868 volts. I'm like, real quick, I just want to go back to this. Remember the steps. Name of the game, solve for the base current. Okay, use Kirchhoff's voltage law to solve for the base current. Okay, those are just know the anatomy of your transistor. Know that this is always going to be the emitter current. This is always going to be collector current. This is always going to be base current. Okay, and then of course, like I said, after you've solved for the base current, you can figure out your emitter current and your collector current. And then after that, if you need to solve for the voltages that are along this like collector emitter like rail, then it's just the name of Kirchhoff's voltage law. All right, so now we're going to get to the fun part, which is where we kind of look at some practical applications of transistors, and I'll show you some example circuits of stuff I've used for transistors for. So yeah, let's just crack open some circuit simulations. Okay, so this first one is a good one to start out with because I want to kind of break down something that might not be so intuitive for a transistor. So right here, just real quickly, we have a current source going into the base pin of 1 milliamp. And then real quick, we have our beta value is equal to 100, right? So that means that this is going to conduct 100 milliamps, which is what the collector is doing. Right. So when we have 1 milliamp flowing into the base pin, that means the current flowing into the collector is going to be 100 times that, or 100 milliamps. So what I think is not very intuitive right here is that I have a 12 volt voltage source, right? Yeah. So 12 volt voltage source right now, and it's drawing 100 milliamps, right? This, and if this were to be like, because a lot of times people tell you, oh, transistors are like switches. Well, if you viewed this as a switch, you'd be like, well, this 12 volt voltage source is just shorted to ground. Like, how is it not a short circuit? Why is it not blown up yet? It doesn't make sense. This is kind of, I'm trying to like break down that intuition, or like that. It's a bit counterintuitive, I guess is what I'm trying to say, that this actually works. Like this will be just fine. And even what we'll do is to go something even crazier is let's just go something like 24 volts. Like I just doubled the voltage, right? Nothing else, nothing changed. We're still getting, well, if you want to know what really did change was this change right here. The voltage drop VCE is what's changing. But just understand that like literally it is a current controlled current source, right? So the current through here is always, no matter what the voltage is at this level, I can make it like 40 volts, 40, we'll go 48, still the same exact thing, right? So literally all that matters, all you need to think about for transistors is in terms of current, okay? So that's like this is like I guess a counterintuitive example that I wanted to show really quick. And understanding like the importance of literally just focus on current, okay? So yeah, like the notes I have is just make sure you understand that the current on the collector is directly related to the current on the input of the base pin times beta. I've said this a bunch. Hopefully it's getting through to you. And like I said, if we vary, oh yeah, we can also vary IB and see how IC changes. That's also a good one. So let's just take this and we'll like go up to, let's go like 2 milliamps. Remember, keep in mind, this is still with a 40 volt voltage source. So 2 milliamps, 200 milliamps is what we're conducting now. And go to something like 500 milliamps, right? That's literally how it works. Current in the base pin is directly proportional to the current in the collector pin, no matter what your voltage source is. Okay, so here's another really good example of how you can use a transistor as sort of like a current sink. So right here, I have a 1 amp current source that is split off, and we have 2 branches right here. We have one branch that's going down into our transistor, and then one that's just going through this 100 ohm resistor right here. Okay, as you see, IB is equal to 1 milliamp, so that means we can sink up to 100 milliamps of current. So if you see, we have 100 amps flowing into this node, we have 900 exiting, and then 100 exiting. So if I vary, if I go, let's say I went like 5 milliamps, then I would sink 500 milliamps, and then this would be 500 milliamps exiting, right? So again, literally just focus on the base current, and that'll tell you everything you need to know about the rest of the circuit, right? So if we know that the base current is 5 milliamps, and we know that, we then know that the collector current is 500 milliamps, and then that will tell us everything else we need to know. Okay, so the next thing I want to point out is that let's say we wanted to sink all 1 amp, the entire like 1 amp of current that we have right here. So this is where I kind of want to talk about is one of the downsides of transistors is that if you want to sink a lot of current, you have to source a lot of current, right? So just keep that in mind for if you're thinking about like when you're like, oh, can I use a transistor to power my light bulb that draws like 3.5 amps of current? The answer is probably no. All right, so these are some of the limitations of transistors, and we'll get into more of this later, showing some of the applications, but I just kind of wanted to demo this fact. Okay, so this next one is a really, really common use of transistor that you'll see like on YouTube, is just to control the current through an LED. And this is actually a pretty good use of transistors because it's pretty easy to control the current through this LED just using a simple voltage and resistor setup. So if you knew like this resistor can only handle like, 50 amps or not 50 milliamps or something, of current, you can usually just start messing around with values and just see like, oh, if I go up to 1K, like, see, we're down all the way to 60 milliamps. So it's very, very simple to do. And so we're controlling a 12 volt voltage source this way. So this example circuit is just a really common use of transistors, and that is to drive an LED. This is an LED right here in the circuit simulation software. So like I said, it's pretty simple to control the current through an LED whenever you know that in order to control the current through this collector pin and the emitter pin, that all you have to do is control the current into the base pin. And so you can just do that with a simple voltage source and resistor setup. So whatever you want this to be, you can just kind of do the math and go, okay, if I want the current to roughly double, 500, and then it's as simple as that, right? So very straightforward use. And then what you can, this 3.3 volt source can typically come from like a processor, like a microcontroller or something. So you can just PWM this signal as much as you want, and control the current through your LED. So this last example that I want to show is a way that we can use a transistor to control the voltage at the input of a microcontroller pin. So that's what this little part of the circuit is supposed to control. And we're measuring the voltage right here. So what we have set up is we have a 3.3 volt signal that's being fed into the input of this microcontroller pin. And we have the collector pin of the transistors connected to this line. Then we have the base pin of the transistor connected to another 3.3 volt signal that I can connect and disconnect with this switch, much like you would just turn it on and off. So the way it works is that whenever this switch is closed, i.e. the 3.3 volt signal is on, then we have current flowing into the base pin, and therefore the transistor conducts, and so it conducts all 3.25 milliamps of current down here, which pulls the voltage at this pin low. Whenever I disconnect the switch, i.e. whenever I turn off the 3.3 volt signal, no current flows through the base pin of this transistor, therefore it stops conducting, and so all the current flows into our microcontroller pin. You can see the voltage is raised to 3.297 volts. And with that, that pretty much wraps up what I wanted to cover in this video. Just some key takeaways that I want to go over is a transistor is a current-controlled current source. So the two key equations that you definitely need to remember are that IC equals beta times IB, i.e. 1 plus beta times IB. Transistors are bad at switching high currents because IB must be proportionally high to switch a high current, right? So they're better at switching lower currents, as we just saw. So, and there's two main things you can do with a transistor that is use them as like, you can finally control the current through the transistor just by controlling the current into the base pin. The other way you can use transistors is just simply as a switch, where you can kind of take a voltage like we saw in that last example and just toggle it high or low. So those are the main uses for transistors in like modern day electronic devices. So thank you so much if you made it to the end of this video, and hopefully I will see you the next